lecture 9 today, I guess. All right. Any questions as I'm preparing? I'm kind of eager to move and teach you the symmetry breaking of non-abelian, the non-abelian case of symmetry breaking. But then I thought of decided, let's finish the U1 case. Let us discuss what I have been arguing yesterday, that the theory we have built actually with the artificial gauge invariance by adding an extra variable is actually gauge invariant. So we are going, so what we are just, if you wish, a summary today from Proca to Higgs. And maybe we could say and back, just to get you, but this is an important direction. You don't ask me questions and I'm worried that there may be confusion. Usually not asking questions doesn't mean that all is clear, at least in my experience. So we said that the Proca Lagrangian, we started with a massive field, and how to write the massive field? Well, you take the massless one, it's called Maxwell, and add the mass term. It couldn't be simpler, Proca says. Just do it, as the Nike commercial. And then I rewrote it after integration by part, and that was 1/2 a mu. You've done this, box plus m square. How did it go? G mu nu. Check on me, please. Minus d mu d nu a nu. Notice the way I'm formulating the theory. There is no more gauge freedom. I have added the mass term. It's a choice of variable. You can tell me, well, maybe you can add more degrees of freedom, change the variables, but in the Proca formulation, it's not that I'm fixing the gauge. From here, we have shown a number of things. One is that d mu a mu is 0. It's not your choice, okay? This is a must. This is a Proca equation. Becomes a constraint. Just by taking a derivative of the equation of motion. Well, let me write. Maybe it's better. I just remind you how we did it. We wrote the equation of motion that you were supposed to check. And from here, by taking an extra derivative, we derived the mu a mu equal to 0. It's not surprising what we got. These are equations of motion. It's very important. And each component satisfies a Clyde-Gordon equation. As we like. The fact, of course, that it's equation of motion is reflected that you can find the propagator uniquely. There is no choice of a propagator, depending on the age. We also got the propagator. You guys did it. And we found out that delta mu nu Proca with the usual normalization a la Maxwell has a minus I q squared, let's call it q today, minus ma squared. And then the g mu nu minus q mu exchange momentum q nu over ma squared. And we didn't like this term. This was bad. This was Proca. Bad at high energy. We could have gone on. There are variations of this that you can do. I don't want to, it's called the Stuckabelig approach and so on. But before or later, you will get stuck. And I don't want to get you lost in the formalism. We said the simplest way out, then one at the end of prove true, instead of Proca to generate mass. So this is called Higgs. From Proca to Higgs. Generate the mass. Generate the mass dynamically, not to put it by hand. And Higgs, that means spontaneous symmetry breaking. So we wrote the gauge theory, which is 1/2 the way I wrote. Let me write symbolically d mu phi squared minus v of 5. I added a scalar field, but I kept the Maxwell massless case. I wanted to have manifestly a gauge invariant theory. And d mu was d mu minus I g. Notice I write g, not t. This is not QED. This is some imagined theory. A mu, as you know, and so on and so forth. I don't want to now bug you. We did think, let's try to summarize what went on. Because of the gauge invariance, I chose the variable phi. Please interrupt me at any point. You know, even if you didn't ask questions now, it's a good time, because I'm sort of just reminding you. I introduce a mass scale called V. In the theory, the sign was crucial. This sign leads to spontaneous symmetry breaking, a sombrero potential, a Mexican head potential, and bottom line, in a nutshell, what happens if I write the variables? Let me choose V plus H plus IG. This is a physical field. This is Higgs. This is physical. This exists. We found out that in order to be able to find the propagator, we needed to fix the gauge. I had an artificial degree of freedom. This does not exist. This is unphysical. And I needed to fix the gauge, so I added the gauge fixing term to Mr. Higgs, which was, I think we did the minus sign. You reminded me, d mu a mu plus, on dimensional grounds, I have to put MA here because I need G to be involved. The sign was chosen here in order to separate, as we found out, A mu and G. And then we found the propagator. I cited it. And that was the D of G is, no, I'm sorry, there is C here. It's very important, otherwise there will be XC dependence that would not allow for the separation. And we had D of G propagator was I, Q square minus psi, MA square. And delta mu nu, it's not Proca anymore. How did I call this propagator? Proca above. Delta mu nu Higgs, or at Hooft really. It's not that Higgs understood that, but that's the Higgs case. Higgs has nothing to do about working out the Higgs theory. It's Mr. at Hooft, and this is minus I Q square minus MA square. The pole the mass of Ma, and then suddenly a good propagator. This is what we've done up to now. It took me what? Around 10 minutes to bring you what was here, Q square minus psi Ma square. I have to pause always to be sure that I'm right. If psi is 1, that of course is trivial. If psi is 0, I should get the transfer. I do. If psi is infinite, I get. So what is Proca? Proca is defined as a limit Q going, not Q, very silly, epsilon going to infinity of Higgs. That's what you get. We also introduced the fermion, if you remember. We introduced the fermion head. Now add the fermion. Fermion is very important. This is the building block of the world in which we live. The world is made out of fermions, quarks, and leptons. And I had a, if you remember, I had a charge of psi L to be a half psi L. Please check. I had the right to choose charges. Is minus, that's my privilege. Notice with these charges, I can write then Yukawa interaction added to the Lagrangian, which is what? Yukawa psi L bar. So that gives me minus a half Higgs psi R plus Hermitian conjugate. By the choice of charges. And what it meant that we got an interaction. Yukawa H psi bar psi minus I Yukawa G psi bar gamma phi psi. This is our central interaction. We are not interested in the gauge in the Higgs field now. There is no gauge dependence. I can forget about it at the moment. Let me pretend it's very heavy. I'll come to it later. I need to worry now about the G field. Once I establish that, I'm going to look at what I want to study now is the fermion scattering. If you don't ask me questions, I will be moving ahead. Fermion scattering. Why? I want to prove gauge invariant. I'm asking, I expect it is, I'm asking a question, you and I should see that. This is what we want to do. So I know how to, gauge dependencies, of course, just to remind you, there is also DH. I don't write it because it's trivial. That this is just a scalar field. It's Q square minus MH square. It's manifestly Xi independent. It's just a massive scalar particle propagating, okay, so I can forget about it. These are things that I have to worry about. How in the world does G know to cancel the psi dependence of A? Okay, that's the task for us. So I have an interaction of the G with the fermion. What I need is the interaction of A mu with the fermion. I must check the gauge interaction. Gauge interaction, of course, comes from the generalized. I add the how shall we call it, the covariant Dirac term. Which is I psi L gamma mu d mu psi L plus I psi R gamma mu d mu psi R. I forgot to say here, this may be important at some point, the mass of the fermion is Yukawa times V, but that you remember, I hope. That's what the meaning of Yukawa is. I couldn't write the mass term because of the chirality. Left and right fermions have different charges. And so here, and I know d mu, where is d mu? Where in the world did I write d mu? Here it is. Has a minus I with plus I, and the charge is a half plus L, so I will get G over 2 interaction from here, A mu psi L bar, gamma mu psi L. It has a charge half, the right-handed guy has a charge minus a half, so I have this. Remember that left-right projectors are 1 plus with my conventions, minus gamma phi over 2. So this interaction becomes G over 2, A mu. What will I get? The gamma mu piece will cancel, and there will be a gamma phi piece only. And that's going to give me A mu psi bar, gamma mu, gamma phi psi. I'm choosing the 4-component notice notation. I like Dirac notation because I'm used to doing calculation with 4-component fermions. I could work with left and right. And we should be able to go from one to another formulation, but the 4-component is particularly useful because the Feynman rules and everything was developed. People did develop the 2-component Feynman rules in recent years. So I have an interaction now. This checks. I have the interaction of the gauge boson with the fermion. That's my, let's call it electron. I have the interaction of G with the fermion. And I want to study the following. I want to study fermion scattering. What does that mean? That I have a fermion with momentum P1. Let's say becoming momentum P2, another momentum with P3, P4, propagates a field with, okay, we'll write that. It also can propagate, in complete analogy, the G field. They are C dependent, so of course, there is a complete analogy. I can write P1, P3, P2, P4. And what is my Q when it appears? Q is, well, I don't have to write identical really, or maybe I could because that's how I defined it. Let's take this to be a momentum Q in this direction. So Q is what? It's P1 minus P2, right? The way I draw it, which is P4 minus P3, I think. Correct? Let's have them here. Let's have them neatly for us here. Let's write them once again, the interactions. I have an interaction. So I have an interaction Lagrangian. There are just two fields for me. G over 2, A mu, psi bar, gamma mu, gamma 5 psi, minus IG. There is a factor of I. And then what did I have here? Yukawa. What did I write there? Yukawa Yukawa, but we know what Yukawa is. It's M over V. Remember that the gauge field has a mass term. I should have written it before, maybe. Even here, MA was, who remembers? It's proportional to V, and it's G times V. So what you have here is, so Yukawa, the file becomes heavy if I write too much. Let's go where Yukawa is. Yukawa is, so where could I write it? I can write it here. Yukawa is M over M psi, if you wish, M fermion over V. I will write M psi. If I forget, okay, if, you know, and I may, M psi, if I forget that's the mass of the fermion, I will write M. But I know that MA is G times V, so this is precisely G M fermion over MA. I could write the Yukawa, but I want you to emphasize that Yukawa actually can be rewritten as a function of the physical quantities that describe the free particles. Okay, the interaction is given by masses. Remember what I keep telling you, the beauty of the Higgs mechanism, that the mass becomes a dynamical parameter. And this is G, if it's not clear. This is the gauge coupling, okay? So why don't I make sure that I write that G, maybe I can write nicer. G M over MA. Let me write capital the gauge boson mass so that I don't make mistakes. And then there is G, and then there is psi bar gamma phi psi. I need interaction. I have the momenta. What else do I need? I need the propagators. Let's put them once again to have them. So that if you do want to look at the notes, it's all here. D of G is I Q square minus psi MA square, and delta mu nu of A is, I hope I have space, minus I Q square minus MA square. The gauge field has a mass MA. And here we have, let me try to squeeze. Maybe I should have written this better. I'm sorry. Let's try to, I do want to have it on the, let's try to use the space better. D of G is I Q square minus psi MA square. Remember, I keep reminding you, this is not a physical field. You can see from the fact that the mass depends on the gauge condition. This is how you know that it's not physical. Delta mu nu is minus I, so there is an opposite sign when we do this. We should not forget minus MA square. And then what do I have? G mu nu plus psi minus 1 Q mu Q nu Q square minus psi MA square. You know, you have hope because you have here the same unphysical piece. And that, of course, it comes with psi minus 1, but maybe this is why it could work. Okay, so we are preparing this calculation. So please ask me if you missed something here so that you can reproduce it. But you got to help me because I can make a mistake. So I have two terms, A and B. Let me start with A. You know, because of when I do the Feynman rules, there is a factor y times an interaction. I don't care about the overall sign. So, okay, let me say it here. I'm going to be cavalier. I don't care. About overall sign. If you do, you will check it. Just relative. I want to see what happens when I add up A and G. So the first piece. There is G over 2 coupling. So it's going to give me G over 2 square. Then let's start psi bar of P2. Gamma mu, gamma 5. Psi of P1. There is an interaction on the, there is also psi bar P4, gamma nu, gamma 5, psi of P3. The product of my two terms times the propagator. The propagator has, I don't worry about the overall sign, but the relative sign. So I will remember that there is a minus sign here in the propagator. So I'm going to write -1 from the propagator. And then there is a propagator, which is, I think I have not forgotten anything, which is G mu nu plus psi -1 Q mu Q nu I want to squeeze it so that it's below the line. Q mu Q nu Q square minus psi ma square. You agree with me? Please, we have to make sure I don't make a mistake. Oh, sorry, there is 1 over Q square minus ma square from the propagator. I think this is correct. Let me write them down and then elaborate them. The B piece, there is a relative I sign. So there is a minus sign from the interaction because of I twice. And then there is G square, M square, the fermion mass over ma square. Agree? And then I have psi bar. There is no gamma mu, so I don't have to worry about the momenta. I can just write, well, okay, just to be sure that I don't confuse you. Let me be pedagogical. This is psi bar P2, gamma 5, psi of P1, psi bar P4, gamma 5, psi of P3, and then there is a propagator. Times I didn't worry about the overall sign, so it's just positive 1 over Q square minus psi ma square. This is what I have. Okay. This is A exchange, and this is G exchange. Minus sign from the interaction, the relative sign would be, I had a minus sign because the propagator has a different sign. Here I have a minus sign because of the factor Y interaction. The rest I think I wrote correctly. So look at the, what shall we do first? Let's do the A piece. Notice that the A piece has two pieces. One which is sign dependent. So let me write it separately and then I'll forget for a while. It's G over 2 squared. There is no momentum flowing in the propagator, so I can simply write psi bar, gamma mu, gamma phi psi, psi bar, gamma mu, gamma phi psi. Now the momentum precisely is irrelevant, and I have 1 over q squared minus ma squared. This is one piece that they're coming from here. Let's be clear here, no Xi dependence. Plus, there is a second piece, G over 2 squared. Now I better keep the proportional to psi minus 1. Q squared minus ma squared. Q squared minus psi ma squared. The second piece. Am I right? Yes. There is a minus sign. Are you watching me, please? There was a minus overall sign there. I need someone to be with me. So there is actually a minus sign here, not plus, with my conventions. Minus a sign. Then what do I have? I have psi bar, gamma mu. No, I have to write this nicely. I'm sorry, I have to use this place, but there is a minus sign. G over 2 squared, minus sign. What did I say? Psi minus 1. Q squared minus ma squared. Q squared minus psi ma squared. And then psi bar P1, P2, gamma mu, Q mu, gamma 5, psi of P1 times psi bar P4, gamma nu, Q nu, gamma 5, psi of P3. No Xi dependence, look. So there are two terms, I, the first and the second term. I just look at the second term, which is Xi dependent. Let's just look at this term. And it has, and let's just now use the following fact. Remember that Q mu is, what was it? P2 minus P1 or P1 minus P2? I don't remember. Where did I write it? P1 minus P2. Now remember that, okay, I want to be really pedagogical, maybe more than I should. Dirac equation, we are on shell, is gamma mu, p mu, psi of p is m psi of p. I can take Hermitian conjugate, I'm pretty sure you know, but imagine that I take a Hermitian conjugate of this equation, I get p mu, I get if I take a Hermitian conjugate, I get psi dagger, P mu, gamma mu dagger is M psi dagger. I can multiply with this with gamma 0, so I get here psi bar gamma 0. Or let me be more precise, gamma 0, maybe you forgot. I'll just add 1, which is gamma 0, P mu, gamma mu dagger, gamma 0 is M psi dagger gamma 0, and I get the equation, which is psi bar, P mu, gamma 0, gamma mu dagger, gamma 0 is M psi bar, and I get the Dirac equation on psi bar, which you probably knew that it was with this sign, but I wanted to be sure. P mu, gamma mu is M psi bar. So here we can simply use the Dirac equation. So for example, if I have psi bar by P2, gamma mu, Q mu is, what did I say? Why do I keep forgetting? It's P1. P1 minus P2 mu, psi of P1. Now notice that the first piece acts on the, it's a Dirac equation, gives me psi bar. Oh, there was gamma 5, I'm sorry, why do you have to get gamma 5? Right, gamma mu comes first with my conventions, gamma 5 later. So notice the first equation, gamma mu anti-commutes with gamma 5. So the first term, notice, will have a minus sign. Because gamma mu, well, let's write down, it's psi bar, P2, gamma 5, gamma mu, P1, mu, psi of P1, minus psi bar of P2, gamma mu, P2 mu, gamma 5, psi of P1. I can use the Dirac equation and notice what I get. Both times I get the mass term. So I get minus 2m psi bar P2 gamma 5 psi of P1. Each of the terms is simply a gamma mu P1 mu. Here I simply used, I just used that, well, I just used the Dirac equation. I use these two equations, this, and of course this. Similarly, psi bar P4, gamma nu, Q nu, gamma 5, psi of P3. Now notice Q is not P3 minus P4, but P4 minus P3. So there will be a plus sign. It's the opposite. Q was incoming minus outgoing, but it is outgoing final minus incoming. Well, outgoing minus on the right-hand side. So there is an opposite sign, which is plus 2m psi bar gamma 5 psi. You got to check on me, because if I make a sign mistake, I'm going to be in trouble. So in other words, what I got, so look, what I got is that second piece of A. I'm doing A. A is the gauge piece, and the second piece, which was gauge dependent. We will remember the first piece when the time comes, which was C dependent, had a minus sign, but I have minus 2m times time plus m, so I have a minus sign times the minus sign, and then I have 2m squared And then I have Q square minus MA square, Q square minus psi MA square. I have psi minus 1. And I have psi bar gamma phi psi square. When there is no momentum flowing, I don't have to write psi p4 minus psi. I mean, here I should have written, okay, just for the sake of completeness, I should have written here, but I didn't. I don't really have to. There is no more momentum flowing. It becomes clear what I mean. It's just a product of two different ones. I think I got the signs right. I had a minus sign from the propagator. I got a minus sign because of the different momenta entering. And I had, what did I miss?
G over 2.
G over 2, that's what I need you for, please. G over 2 square was here. So 2 got cancelled, which is what I like. This G would have trouble me. So minus and minus gave me a plus. So I have G squared, psi minus 1. God, I hope I did it right. Q square minus MA square. Q square minus psi MA square. Psi minus 1. I can write it also here, psi bar gamma phi psi square. That's the second piece. There is a G contribution that I have written somewhere above. Where was this? Here it was. It had a minus sign, it says. Oh, here it makes me nervous now if I made a mistake. It says that there was a minus sign G square, M square. That was our coupling. The minus sign because of factor Y. The coupling is GMA over MA squared. So this is good. Oh, I forgot something here. Again, please watch me. There is M squared. And then there is a propagator. Okay, let's go back and check the signs. The B piece. There is a minus sign. There is a propagator. And the same interaction, which you would write psi bar P2, gamma 5 psi P1, and so on. But I can write like this. Interesting what we are getting. Okay, so in other words, when I sum them, A part 2 plus B, so this is my C dependent effective interaction, scattering amplitude. Is given by what is common. I have G squared, M squared, Q squared minus psi MA squared. I think this is common and the only thing that are common. Am I right? No, there is more which is common. Psi bar gamma phi psi squared. Is it true? Yes. There is G squared, there is M squared, there is psi bar MA squared, there is Q squared. Okay. So the first piece, the gauge boson piece, had a plus sign apparently, has a psi minus 1, and then Q squared minus MA squared. If I get the right minus sign now wrong, I will go crazy. I refuse to go on, I go, you stop at me tomorrow. Or maybe you help me find the sign. And the second apparently should be with a minus sign. And what is this? M square I took out. There is simply 1 over MA square, I'm claiming. It seems it should be this. Looks good, right? What do you think? Should we make bets? At this point, you know whether I'm going to make it or not. I think it looks good. So what is this? And I have C minus 1 MA square minus Q square plus MA square. I think this is correct. Let's go on. Notice that MA square cancels, please, the second piece and this piece. And I get G square, M square, Q square minus psi MA square. What do I get here? I get psi MA square, my first piece, minus Q square, divided by Q square minus MA square, MA square. I made it. Yes, we can. With a minus sign. Now when I cancel it. Manifestly, sorry, psi bar, gamma phi psi square. The psi dependent piece, psi independent, is G square, M square, MA square, a dimensionless coupling. Of course, a propagator, a very interesting propagator, looks like Q square minus MA square now. It's clean. And there is the axial interaction, which I'm not surprised to get. And there is a minus sign, not so important for us, okay? But okay, it came up with a, I can't trust this minus sign. I never worried about the true Feynman rules and so on, okay? So this is not relevant. The way I computed, right? The interaction is, it's very interesting, okay? He has a beautiful form. I had a chiral symmetry question, I had chiral interactions, and I got a chiral, manifestly chiral result, gamma 5 here. Okay, this is due to the chirality of the whole thing, chiral theory. I had my dimensionless, this is my Yukawa coupling, if you remember. So really what I have here is, it's another way of writing it. The thing here would be a Yukawa coupling, 1 over Q square minus MA square, psi bar, gamma phi psi square. Since Yukawa is G, notice this formula. This is a beautiful formula. This is what will happen in the standard model, up to a factor maybe. This interesting thing that Yukawa couplings are related to gauge couplings. All you have to know is the masses of the particles. And therefore, the relative physical processes are interconnected. So, QED. I have proven to you a theorem. We have proven psi independence has been proven to me in one example. Maybe we'll do one. We are not going to do the loops and so on. You can, you know, sometimes we can. We'll talk about that. But I won't do it explicitly in class. You can see the magic, the non-trivial thing, okay? Psi independent has been proven to all orders in perturbations here. Just like in QED by Dyson. is a very sophisticated thing. Our modest tree level, okay, should encourage you to believe that, in other words, I can work. You see, now I know what was wrong with the unitary gauge. The propagator is bad, but the physical result will be the same. If you knew how to calculate, you will get the same physical result of the unitary gauge. By the way, since the unitary gauge, so I have a little exercise for you. Compare with you directly unitary gauge. Of course, you should get the same result because I've just proven. But just do it for fun if you're in the, I would do it. I like to do these things when I'm studying. I get an understanding when I do a few examples. Okay, it sort of enters, you know, it becomes a part of me. So it's a neat exercise, not trivial. You can decide whether you want to ask questions. If not, we will have a break because I want to study this result. I don't want to just compute it, okay? I want to show you the importance of not stopping after they do the calculation, okay? I'll talk about it later. So if there is no urgent question, okay, then I want you to sort of, I mean, sometimes the students I've noticed don't even want the break, okay? But I think it is extremely important that you refresh yourself and just spend a few minutes thinking whether there was something non-trivial here. Probably not, because it was straightforward, but just in case. Let's meet then at 12. It's 11:54 on my clock, so let's meet at 12. Okay, it's 12 o'clock according to my total amplitude. Therefore, for FF scattering, Fermion scattering, proportional, I don't care about the overall coefficient. I had the piece 1. Let's go back and retrieve it. Where was it? Where did I have it? No, that's number 2. So I need number 1. Here it is. It had a minus sign. Okay, there was one piece. It is sort of, it has a minus sign. G over 2. I'm sorry, I have to be sure. I think it's G over 2 square. So we can look together. Yeah, G over 2 square. I will just write symbolically. You see, there is a vector piece, axial vector piece, that's exchanged of there has to be there. It cannot be only scalar, or better to say pseudoscalar. And then with this, there was a minus sign. So it's the same sign. I don't have to write the minus sign. Good. And then there is a second piece, which is, I will write it in the manifest Yukawa mass dependence. I won't write Yukawa, I will write the same m square. So m square is m Fermion square, if you wish, m phi. We can have m phi as we wrote sometimes. And what else? There must be the same q square minus ma square. What is propagating is a physical particle of mass ma. G was not physical, that funny psi piece cancelled, we knew, and that has psi bar gamma phi phi square. This is what we have computed today. I could have worked in the unitary gauge. You see, if you work in the unitary gauge, there will be 2 pieces, one from G mu nu in the unitary gauge, the first piece, and the other will come from K mu of the A propagator. Okay, this is just an exchange, of course, of a massive Proca field. At the 3 level, they must have. I can do the calculation of the massive Proca field with a propagator, delta mu nu, proportional, just for you to see, q square minus ma square, as you know, and then g mu nu. That will give me the piece number 1. This is what I called piece number 1. And then there will be q nu. I can write this more neatly. Using Dirac equation, the second piece will give me the second piece here will give me the second piece. So the first piece, this will be the first one, and there will be the piece 2, obviously. The first one is manifestly axial current times axial current, because that's the exchange of a gauge boson. The second one also looks like the exchange of the gauge boson, but because of the Dirac equation becomes basically a scalar, a pseudoscalar interaction. Now, so what is the theory? This is a theory of a massive gauge interaction. And of course, in the Higgs formulation, it's associated with the spontaneous symmetry breaking of gauge symmetry. It becomes Proca. And that was, the Higgs formulation was done when my gauge transformation was a function of space-time. It was manifestly gauge. But there is also Nambu-Goldstone that I talked about. What is Nambu-Goldstone? It's the limit when alpha is constant. In the Higgs case, I can often call it just H. What I have, a massive gauge field, but no G. In the Nambu-Goldstone, what do I have in the Nambu-Goldstone? And G. No A. But G is there with mg equals 0. This is very important to keep, this is essential to understand. So I have a question. If it's true that in the Nambu-Goldstone case, I have a Goldstone boson and G disappears, how shall I get that? So my question is, how to go from Higgs to Nambu-Goldstone? This is often called Goldstone. I'm trying to remember to use Nambu. Actually, most of the time, even I forget, just to give credit where credit is due. How to go from Higgs to Nambu-Goldstone. You see, what I'm trying to give you here, this you don't find easily in the books, okay? I need you to be concentrated. Someone may do it, but I don't find it in almost any book on field theory. And I was always puzzled when people teach me, okay, they tell me, look, there is a massive gauge field, but in the other case, of course, you accept that. But how do I see that when I'm doing a calculation? In other words, I computed here an exchange of the massive gauge field. But when the gauge transformation becomes the global one, when alpha is a constant, I should get a massless, instead of having a massive gauge field, I should have a massless scalar particles. So what should I do? What is this limit? Alternative question, right? What is Higgs going to Nambu-Goldstone limit? What is it? What should I take in my calculation to get to this limit? So maybe even more important, this question. What is this limit? Well, it's equally, sorry, it's the same thing. I'm repeating myself to overemphasize. That's the way I am. I want you to, I want you to capture the essence, okay? So the things that I keep repeating are the essence, and I want you to, there are a few messages that I want you to take out of this course. You will forget a lot of it, but I hope the basics not. Well, remember how I go from Nambu-Goldstone to Higgs. Remember what I do. It's very simple. I take d mu becomes d mu, right? From global to local, all you have to substitute. So what is the limit? Of Nambu-Goldstone from H? Well, it's obvious. I can't take Q equal to 0. What does it mean? The guy carry charge. And it doesn't make sense that I take A mu to 0. Okay, I want to be able to do the calculation. Obviously, the answer is G equal to 0. if I'm right, and it seems obvious, why? Because in this limit, d mu goes back to d mu. So you and I should retry. In other words, by taking G equals 0, I should get Nambu-Goldstone picture. So let's do it. So I'm going to take this amplitude, okay, with your help. You help me. What happens when G goes to limit? I have two pieces, 1 and 2. So we'll separate them, the piece number 1. So my amplitude m squared had a piece number 1 plus piece number 2. What happens to piece number 1 when G goes to 0? Who's going to speak? We have to do this together. What happens to piece number 1? When G goes to 0? Someone
Just 0.
Sorry?
It goes to 0.
Yes. I find immediately in that limit, I goes to 0 when G goes to 0. Very good. This is important. I don't have to worry about that. By the way, I'm happy that this happened because this was an exchange of a gauge field. It better go to 0. In the Nambu-Goldstone case, there is no gauge field, okay? So now piece number 2, let me write it again, just to be sure that we are doing something highly non-trivial. Piece number 2, let me remind you here, is G squared, m squared of the fermion, ma squared, 1 over q squared minus ma squared psi bar gamma 5 squared. So what happens to this when G goes to 0? And now G goes to 0. What happens? I need help.
There also MA goes to 0.
Very good. It does not go to 0. What is important to remember here that MA is GV. That also goes to 0. Very good. So in other words, 2 goes, look what we get. 2 goes to m squared over v squared. MA goes to 0, so I get 1 over q squared psi bar gamma 5 psi squared. What is this? Look at this. This is a propagator of a massless particle. Scalar, actually pseudoscalar here because the interaction is pseudoscalar. What is this? This is some Yukawa coupling I can call. In other words, this here corresponds completely. There is a perfect analogy with an exchange of a particle who interacts with m over v. This exchange, you see what we have proven? We got the Nambu-Goldstone boson. And this is really the beauty, the way it works, okay? So you can really see that there is this profound connection between the Higgs and the Nambu-Goldstone mechanism because mg is 0. And it has a pseudoscalar interaction. Because it has a pseudoscalar interaction, this checks with this, I get it twice. Because mg is 0, it will check with this. And because of the coupling is m over v, it will check with this term. Up to the sign, which I didn't worry about. So in other words, what we have proven, in other words, the final result, let's just see the final result, what we want. M squared amplitude due to the A field goes to the m square amplitude of the massless G field. This is massive A. And this is massless G. When G goes to 0. When G goes to 0, the gauge boson decouples. See, now you understand what is the global symmetry case. That's just the coupling of the gauge boson. It doesn't mean that there is no gauge boson. Who in the world knows? There could be billions of gauge bosons. If they are not coupled to us, we don't care about them. For us, they don't exist. They may couple to someone else, but if they don't couple to us, of course, if they couple to someone else, eventually there is gravity, and you and I are all connected with anybody else in this universe because of gravity, but we are ignoring gravity. It's very weak. So at this point, these are separate worlds. And it all was based on this beautiful result that MA is G over V. This is a central thing that is very important here. So that this goes to 0. When G goes to 0, this is very important. This is what the Higgs mechanism told us. All the particle masses go to 0 when their couplings go to 0. So the only way for you and me to get a mass is to couple to the Higgs. But it's interesting, we are very massive. We don't really couple to the Higgs. Do you know why we get a mass, you and I? How we get a mass? What is our mass coming from? When the Higgs was found, there were articles in leading newspapers. Even some well-known physicists, I won't give you their names, were claiming that the discovery of the Higgs gives us the probe of our masses, okay, which is completely wrong. Completely wrong. Remember what I said, there is this guy Proton. And it's made of some funny up and down quarks. There is also neutron. Remember what I told you, M proton, you knew that, is basically equal to M neutron, okay, almost, which is like GV. But M quark, UD, they are not the same mass, roughly. It's few MeV, which is so much smaller than M proton neutron that I can basically take this to 0. Assuming that it's correct what I told you, that up and down quark mass is a few MeV, we'll talk about the masses, you're gonna trust me now with this result. So in other words, where does the proton get the mass? So M proton and neutron, where does it come from? We didn't discuss QCD, but you must have heard, and maybe Alexei said a few things about QCD, right?
Yeah, from the gluons.
Well, from the glue, right, from the gluons, but not just from the gluons. Actually, it comes from the quarks, but not from their mass. You see, these guys inside here, UD, they are not like some static objects, okay? They are moving crazily inside. They are very strong interactions, and there is an incredible dynamics inside. Think of yourself running like crazy, or think of your, no, maybe that's not what I want to say. No, I don't want to give the analogy, okay? So there is an enormous kinetic energy. And the answer is from kinetic energy. Or whatever is inside. And so this means of the up and down quarks, and of course, thank you, glue, as we say, gluons, the gauge bosons of the strong interactions. Okay, there is a beautiful dynamics that has to do with the fact that there is this strong interaction that doesn't let them just being static. It's sort of interesting that elementary particles, that we found the origin of elementary particle masses, and that's irrelevant for the world in which we live in. That's kind of ironic. So in the world of elementary particles, there is something divine about the Higgs, right? It gives the origin. People used to call it God's particle, right? You probably know the origin of the name God's particle. Why? Someone may tell me why it was called, and sometimes still called, God's particle. Anybody knows? Lederman, who's dead now, a great experimentalist, the ex-director of Fermilab, the Nobel Prize winner, discovery of B quark, actually the co-discovery of parity violation as a young man. Amazingly, he also co-discovered already in 1957. He died only some years ago. He must have lived in his 90s, okay. He wrote a popular book. So in his popular book, you know, he didn't know how to call these Higgs particles. You know, everybody was upset. People have been looking at it for years and years and years. We should understand why we had to wait so much for the Higgs. So he calls it, God damn it particle. And the editor says, you cannot say God damn it in a book. You cannot curse in the book. So they say, no, you cannot do that. But you, and then they said, okay, you can call it God's particle. Okay, there was a joke. And it was picked up by media. So all that he was complaining that this particle didn't want to reveal itself. Remember what this crazy thing about the Higgs, suggested in 1964 and discovered in 2012, Higgs. This is birth. And this is observation. I wonder if someone asked you already, but it's too early from what I said. Let's wait. I will ask you later why it took so long to discover the Higgs. Okay. We'll have to do the standard model version of the. This is a side remark. I'll try to say a little more about QCD in due time. It's not easy to find time in this course. Teaching standard model is an art of making a choice of what. So I try to teach you what is easier to learn so that you can take with you. The course is too short. It should be actually 2 semesters at least, not 1. Okay. This may not be clear for those of you that don't know that there are gluons and so on. Okay, then you just relax. I will talk about it, even if I don't go into details. Okay. I think I have nothing to say here anymore, unless you ask me anything. I just want to sort of start. I want to give you a flavor of what happens. We took the U1 example, and now from U1 we have to go, which is abelian. We have to go to non-abelian. That's our task. This was just an illustration. After all, remember in the standard model, G standard model is SU2 cross U1. I'm not writing the strong interaction because we won't break it and we don't care about it at the moment. And what is the symmetry of the world? let's call it G nature, is the symmetry cannot be true SU12 cross U1, which is the symmetry which is unbroken.
It is U1 electromagnetic.
U1 electromagnetism. Thank you. Sorry that I want you to say a few things. I just need you to be with me. Normally, you know, I thrive on audience and I like to see you in the class. I want to get you all right. So you see what is broken really. SU2 is broken, not U1. It's just reshuffled. Really, the meaning of this is that SU2 is broken. Not U1. We don't have an example of U1 spontaneously broken symmetry. There are speculations of having extra U1 symmetries, but they simply we don't have any evidence in nature. So we have to, what we have to do, in other words, what you and I have to do is to study the SU2 gauge theory. Let's not do SU2 cross U1. I even tried to teach you the standard model. I started with SU2 first. You always do the minimal thing. SU2 gauge here. Which means which is equivalent going from, this is equivalent going from Maxwell Lagrangian into Young-Mills Lagrangian. So let's start with that. In the Maxwell theory, it's based on in the U1 case, d mu is d mu minus I in this case, d mu is d mu, for example, electromagnetism, that would be precisely E Q A mu. Whereas here, d mu, if I have an SU2 symmetry, must have a coupling constant associated with SU2. Let's call it gauge coupling G. How many generators? 3. That means 3 gauge fields. This is what means going from U1 to SU2. Q, of course, Q meets with itself in the U1 case, whereas TA don't. Well, they commute with themselves, but not among each other. That's why I have the anti-symmetric tensor. So any interaction with anybody Fermion on a scalar, it's very easy. You just substitute the covariant derivative. That's done. The only difference is here that you introduce the gauge field F nu, which is d mu a nu minus d nu a mu, which is a gauge invariant quantity. And here, of course, if there are 3 A's, there are 3 F nus. Who remembers their form? You studied this, you told me. Is it like Maxwell?
And there will be a term from the commutator.
Right, so, right. There must be this epsilon ABC, right?
Yeah.
This is the crucial thing that makes all the difference in the world. Extraordinary what a little thing like that can do. once, of course, well, it's sort of, I'm writing again. I'm sorry that I'm being so silly that I want to use the space, but while I'm writing, you can think. Okay, let's make the, we are separating these two worlds. So F mu nu A is d mu A nu A minus d nu A mu A plus G epsilon A B C A mu B A nu C. Because they carry charge, you see they carry charge. The gauge bosons are here coupled to generators which do not commute, therefore they carry their respective charges. It's just the name of SU2, and therefore F mu nu A is not invariant. It will transform as F mu nu A under small transformations plus epsilon ABC. It can be lower index. If there is a gauge transformation, there will be theta B F mu nu C, something like this. This is the gauge parameter, the rotation parameter, whatever. What is U? Just in this case, U, I can always introduce a U1 generator, a U1 transformation, which is E to the I say theta Q electromagnetic. And here I will have U is E to the I. We can be more systematic. There are nicer ways of writing it, but I just want you to capture the crucial thing are this. This interaction of gauge bosons is very important. I'm not going to pay attention to it now. I need to understand how these gauge bosons couple to my matter fields. I have to construct the standard model. Okay, this will be secondary but important. I will come to that later. I will keep in mind that they interact. So in other words, here, if I keep this, the Maxwell Lagrangian is minus a quarter F mu nu. It's very easy to generalize it. Young-Mills Lagrangian will be minus a quarter. You just say, well, sum it over. It's a product of two vectors. They are vectors. They have the three component. You know that vector times vector is invariant. So it's very easy. Everything goes through all the formulas. You see a covariant derivative, you write the same covariant derivative. If there are 55 generators, you will include the 55 generators. The only thing to remember is that there is a new piece. It won't matter for like 4 or 5 lectures. It won't matter at all. Becomes relevant only if I'm interested in this non-trivial interaction of gauge bosons with gauge bosons. But everything else, all the analogies goes through. We have perfect analogies here. We have analogies here, modulo this extra piece. We have analogies here. We have analogies here. And we have a very important analogy here. Okay. So if I want to study the SU2 breaking, I don't know if I should go on today. Well, I can just start so that I can tell you, I can talk to you. So I want to study the SU2. Let's do the SU2 gauge theory, as I said. Let's go to the Higgs immediately. We can come back to the Goldstone boson, to the Nambu-Goldstone picture. So I need the SU2 gauge field, the SU2 scalar. The Higgs, the analog of the Higgs. There was a complex field in the U1. What should I take? What is the minimal representation? I always want to do the minimal representation. What is the minimal representation of SU2? The smallest representation is a doublet. Which means that phi transforms into U phi. Here it is. I wrote before, all I need to know the form of TA, and these are Pauli matrices. This is the meaning. So how would it Lagrangian look like? We can worry about the fermions later. I'm just introduce this scalar field, Lorentz scalar. It will be d mu phi dagger d mu phi. You agree? It's dagger now because it's a doublet. It's not star. I could write some potential. And then I need to write, look, it's basically the same Lagrangian as before. And if I'm studying symmetry breaking, I don't have to worry about, I didn't worry about Maxwell at all. That was when I, wanted to see the propagation. Okay, they will come to it. By the way, the free piece is the same. The free piece comes when I ignore the interaction in the F mu A, and it has precisely the same form. So there is no difference. Each of these A fields propagates the way the photon will propagate. If they become massive, they will look like Proca. There'll be 3 of them. That's the only difference. So see how it is. How will the potential look like? We won't do the symmetry breaking. We'll just stop now in a few minutes. There is some constant. In the UA case, I wrote phi star phi, 5 absolute value. What should I write now to make it invariant?
Phi dagger phi.
Phi dagger phi. This is it. And d mu, let me write it once again, just but you know what it is. D mu. But let's be complete. It's d mu minus Ig. I don't need the form of F mu A at the moment, but I need to keep this always in front of my eyes. I have one last question. I stop here in a few minutes. There is a little subtlety. This is true that this potential is invariant. But when you have a doublet, if phi is a doublet, so phi is a doublet, so that phi goes into u phi. Of course, trivially, phi dagger phi goes into phi dagger, u dagger, u phi. And u dagger u is 1. I mean, that's, I should have said it. What is u? It's a unitary transformation. U dagger is u dagger u. Dagger u is 1. And we will also choose determinant. U is 1, as we talked before. That's why it's Pauli matrix. Okay, and this is, this in your sleep. This is surely invariant. What is an invariant? It's a spin 0 state. Phi is a doublet spin half. I form the spin 0 state. This carries no spin. Lagrangian can carry no spin. How do I get spin 0? I take anti-spin half. So I take here spin half plus half. In a sense, I take here a spin minus a half, if you wish. It's an anti. That's what I mean. And this is invariant. That checks. This is why this is my term in the Lagrangian, okay? But there is another way of making an invariant. I'm gonna call this invariant, I will call it Dirac-like. It's very funny because Dirac, what does Dirac has to do with SU2? You will understand later. How did you used to get spin 0 in quantum mechanics? You know what a doublet is, if you wish. I can write the phi like this. I could write some phi up, phi down. I don't know, there are many ways of writing it, or I can write up or down. Okay, these are not quarks. I can also write like this, upper and lower. So what is the S equals 0 state in quantum mechanics? Without using phi dagger, what did you used to do to get spin 0?
So it will be up tensor product down plus down tensor product up.
No, not plus. No, there's going to be a triplet. You anti-symmetrize.
Yes.
Spin 0. Very good. I'm glad you tried. This is, you must anti-symmetrize, anti-symmetric. You know what really we are saying, that if I have a doublet, which is 2 component, okay, so this is one doublet times another doublet. That's 4. What is it? It's 3 plus 1. This is anti-symmetric. And this is the symmetric state. This this S equals 0 state, which is up, down, minus down, up, I can write as phi transpose. Notice epsilon phi. Epsilon is an antisymmetric matrix. You agree? This is precisely what I'm writing. This is also invariant. This is phi transpose. I can write it in another way, I sigma 2 phi. This is invariant. This is, well, you know from quantum mechanics, what really happens is, why is it invariance? Because phi transpose, I sigma 2 phi, goes into phi transpose, U transpose, I sigma 2 U phi, which is phi transpose e to the I theta sigma A over 2 transpose I sigma 2 e to the I theta B sigma B over 2 phi. Now notice what happens here. I can move I sigma 2 here. And then I use the following fact. The sigma 2 is 0. Sigma 2, sigma 1, or 3, sorry, is anti-commutator is 0. But sigma 2 transpose is minus sigma 2, and sigma 1, 3 transpose is sigma 1, 3. And therefore, what you get is that phi transpose, this you know from quantum mechanics, I'm just writing you in a fancier way, goes into phi transpose. I sigma 2 will go to the left. And what will happen here is sigma 2 term, because it's antisymmetric, you will get e to the minus I theta A sigma A over 2. Because 1 and 3 anti-commute, so they change the sign. Sigma 2 commutes, but it's antisymmetric. And then you get e to the theta B sigma B over 2 phi. This is U dagger, U, which is 1. In other words, this is phi transpose I sigma 2 phi. I'm checking for you. You should know this in your sleep. My problem is when I teach the standard model generation after generation, I see that you know a lot of group theory, but not SU2 really. I hope I'm wrong and you really know SU2 very well. We'll see. I will be asking you questions. Okay, this is what knowing SU2 means. Being able to write all the invariants and understanding this combination of spin. So my question is, so this is invariant. Why don't I include it? I didn't write it. because it's 0. This is a scalar particle. This would give me spin 0, but it is really 0 because phi transpose epsilon phi, which is this, which is, remember, there is phi up. I can write like down again to emphasize these are scalars. This will give me phi up, phi down, minus phi down, but these are bosons. This is 0. They commute. If this was a fermion, it wouldn't be 0. This is very interesting. For fermion, this is very different. So I have to imagine it for a while. And this is why you keep it in quantum mechanics when you have a fermion and you're talking about spin in a sense of the Lorentz transformation property. Here I'm talking about SU2. When I talk about spinor, this is scalar under Lorentz. It's just under spin. Under SU2 is that. So this is that we are lucky, you and I. There is just one invariant term. So our potential gets simplified dramatically. There could be even other terms. We say, for those of you who don't know field theory, the thing is that SU2 has rank 1, only one element of Cartan subalgebra, only one generator that commutes with itself, with other generators. That means with itself here, by definition. And therefore, there is only one invariant. And this is what we are going to study, and this is where I will stop today. So that we stop on time. Refresh yourself, now stare at this, please, here. Refresh yourselves with the SU2, because we are gonna start from here. You have to be really sure that you have a control of the group theory of this Lagrangian. This and such Lagrangian will be the study of a few extra lectures. Any questions?
Excuse me, Professor.
Hello, yes. Is there a question?
Yes, please. What was your conclusion about where proton and neutron get their masses from?
Our masses, of course, come from masses of proton and neutron, because electron has almost no mass. And what we said that what it is proton guy or neutron is a violent state of quarks plus gluons that move like crazy inside. They carry a lot of kinetic energy. Because of the strong interaction, they're constantly scattering on each other. It's not that you have just 3 quarks. You can imagine in quantum mechanics, you can't have it just a particle, right? If I have an electron, if you think that I have an electron, as you know, around the electron, there is a cloud of EE bar, of course, the same bar. And so we have these clouds of, you have up plus down, and then you have clouds of UU bar, DD bar, and all these clouds and gluons. And this is what came as a great surprise, that the kinetic energy that comes from the QCD is actually fits this is the task of QCD, fits the value of the proton and neutron mass. In other words, these quarks are almost massless. Remember, the mass is few MeV. Now, what is MeV? It's 1,000 times smaller than GeV. So for you and me, we can even go to the limit of M quark is 0. That limit is good. This is a good limit. You know, understanding physics, immediately you put all the effects which are less than 1% to 0. Otherwise, you'll never be able to do physics because there are constantly some corrections. So, and therefore they are massless, so the energy must come from kinetic energy, and that fits beautifully. It would be nice if I had time. I mean, this is something that Alexei should have talked about deep inelastic scattering. He must have talked about it. Who's going to tell me that he did or he did not? How do I know that there is a quark inside why do I say that there are quarks inside a proton? So if there is a proton, and we say that there are quarks here, how do we know that? After all, nobody has seen a quark. You can't isolate a quark. I mean, sorry. Nobody has been able, quarks are confined. So what do I mean by that? There are no free quarks. Why do we say that there are quarks?
By studying the internal with the scattering, high energy scattering.
High energy scattering, right. We do the same thing that Rutherford, well, it was not Rutherford understood it. It was Geiger and it was his students that did it. So what we do, we hit this with an electron, fast moving. And when Q is very large, if Q is much bigger than M of the proton, so that's what I mean, fast moving electron, large momentum transfer, large Q. Q is much bigger. That, of course, by uncertainty probes the distance, which is much smaller than the proton size, of course. You have a good, microscope now. This is what it is, a fast-moving electron. Now you can see, if the electron is moving very fast, so I have this electron coming in with enormous energy, the bigger it is. Imagine at LHC. I can have electrons which have the energy. Well, there was a Hera machine in Germany which was doing this precisely. Okay, there was the EP machine. This is ideal. So think of Hera, and you have an electron, I don't know, with 100 GeV, it's much, much bigger than the mass of the proton. So what you're doing here, you are seeing inside. You are now looking at the very small distances, much smaller than MP to the -1. And there what happens is, okay, Pn behave as if made of almost free quarks. That was the first approximation. Then you do better calculation. When I say almost, actually, you can do corrections. They are not free, really. They are corrections. And that works even better from interactions with gluons. There are gluons also inside and so on. At very high energy. So you can say, how can I do these interactions? I mean, strong force is strong. The answer is that coupling constants, alpha, are the functions of momentum. Constants are not constants, they are function of momenta. When Q is much bigger than n proton, there is a beautiful thing, it's called asymptotic freedom. I stop here. Alpha strong, alpha QCD, say, is actually much less than 1. This is beautiful, it becomes weak. It's called asymptotic freedom. I will tell you a few words about it. I can't teach you. This was a course in field theory, but it's very important, okay? The strength of the coupling depends on the distance or the momentum. So you can do the thing anyway. In the first approximation, they behave as if they are made out of quarks. That's why we believe in quarks. That's called deep inelastic scattering. Deep inelastic, why is this? Deep inelastic scattering. When Q is very large, over me, this is called deep inelastic. You don't produce, you can scatter on the proton and get all kind of junk, not just elastic. When Q is very large. Okay. I hope I found some time to remind you of this that Alexei talked about. I know that he discusses it. Look, I tried to say it in a few minutes. Obviously, I'm going overtime now. There is a question, so of course, who is not interested can leave. But I told you I'm willing to answer any kind of questions like this. You know, so tell me, write to me when you want to discuss. Okay, I won't say anything here. I could speak forever, but I don't want you to get confused. Just tell me if there are any other questions. It seems not. So we can stop here on this note. Okay, guys, take care.
Thank you.
See you tomorrow.